Hello, welcome to part 2 of Chemistry Paper 2, Edexcel 2018. Okay, so this is where we got to last time, was the empirical formula. So we're going to move on from that. So that's where we were last time. Let's go. Part B. Sodium reacts with water to form sodium hydroxide solution and hydrogen. Complete the balancing of the equation for this reaction and add the state symbols for each substance. Okay, so let's think about state symbols first of all. Sodium, so at room temperature, solid. H2O is water, so actually it's quite unusual to get an L for liquid. NaOH will be aqueous. Okay, so it's in solution, and hydrogen is a gas. Okay, so let's look at the balancing then. Okay, so we've got Na to Na, so H2 to H2. So let's have a think about that side. We've got how many hydrogens? We've got 2 hydrogens here. There's no number in front of that, so we don't have to do anything to that one. 1 hydrogen, 4 hydrogens. Okay, so we need to put a 2 in front of this. So we've got 2 times H. Okay. In exam, I'd always advise to do some pencil first of all, and then go over in pen when you're sure you've got the answer. Because sometimes it needs a little bit of rearranging, but you can do it in pencil first and then go over in pen. Okay, so because I can rub this out if I need to. Do it on the computer. So 2 NaOH, so you've got 2 H, 2H, 4, 2 oxygens, 2 oxygens, that's fine. Now we've got to sort out the sodiums. 2 sodiums. We've only got 1, so let's put 2, and we're actually done. Okay, we're done there. So we've got 3 marks. That's nice and easy, wasn't it? So you have 1 mark for just putting that in front of the Na, 1 mark for doing that, and then 1 mark for the state symbols. Okay, you need to do it in lowercase as well, because I've got a note here on my mark scheme that you need to do it in lowercase as well. Okay. In an experiment, equal size pieces of lithium, sodium, and potassium are added to separate samples of water. A flame is produced only with potassium because, you probably can guess, so it's quite, sometimes you get a flame of sodium too, so it's not, I'm just going to say that it's not because it's just because it's flammable, because they all are actually. Sometimes you get a flame of sodium, and it's because it's the most reactive. Okay, let's go on to the next one. Explain in terms of electronic configuration, so how the electrons are arranged, the increase in reactivity from lithium to sodium to potassium. Okay, so increase in terms of electronic configurations. Okay, so lithium, sodium to potassium. Okay, so the atoms, okay, become bigger. Okay, so atoms become larger, so the whole atom becomes larger. So atoms, remember these are group 1 and they lose their outer electrons when they react. Okay, so atoms become larger. And the outer electrons become further away from their nuclei. Okay, this means they are lost more easily, or they're more easily lost. They are more easily lost, doesn't matter which way around you write that, more easily lost and more reactive. Okay, that's why. Next question. Okay, so we need combustion, looks like. Ethanol can be used as a liquid fuel. So ethanol is alcohol, type of alcohol. A student investigates how much heat energy is released when a known mass of ethanol is burned. The apparatus is shown in figure 3. I've done this in class with students. A known volume of water is placed in a metal can. Okay, the temperature of the water is measured. The ethanol is ignited. Ethanol is like a spirit burner, so it's like a glass container with a wick. Okay, the spirit burner. Right, so the ethanol is ignited and placed under the beaker. So the ethanol is in there. So the flame is touching the beaker. Okay, so the water is heated by the flame. The flame is extinguished. The final temperature of the water is measured. Okay, it doesn't say how long they're doing it for, a certain amount of time. So the theoretical temperature rise for burning a given mass of ethanol is 82.4 Celsius. In the experiment, the actual temperature rise for burning this mass of ethanol was only 34.8 degrees Celsius. One reason why the temperature rise is less than expected is that the ethanol does not burn completely. Give a reason why, even if ethanol burns completely, the actual temperature rise is much less than the theoretical value. Okay, so there's not really any insulation going on there, so that heat is going out here too, isn't it? So it is the heat energy escapes or is lost. So heat energy is lost to surroundings. It's a bit like if you sit in front of a heater, isn't it? It's not just heating you, it's heating the room too. So it's not just heating you. So the energy is going into heating the room too. That's why sometimes obviously people have like a smaller heater than one in the corner of the room, because it's just wasting energy. You don't really need to heat anything else apart from the person sitting there, like near it. Okay. So part 2, explain how the method described above could be improved to give a temperature rise closer to the theoretical value. Okay, again, I said about using a lid, or also, yeah, also that didn't have a lid too, did it? That's just open as well. Okay, so yeah, we can just put a lid on it. Okay, so that's lots of questions involved here. So add a lid to the beaker. It's escaping from the water too. That's why it's such a difference. So it's escaping a lot of places. Okay, so less heat energy escapes. Okay, 1 mark for saying a lid, 2nd for saying less heat energy escapes. Okay, it's not saying, isn't it? Like you're in a kettle, you have the lid off. So you wouldn't do that because, yeah, all the heat would escape, wouldn't it? To the surroundings, you're heating the room. You won't be heating the water, wasting energy there. Okay, so you don't want to waste energy. Number 1, obviously, it's not very economical. Number 2, it will cost you more money as well. Okay, the amount of heat energy used to raise the temperature of the water by 34.8 degrees Celsius can be calculated using heat energy is 210 times temperature rise. Calculate the amount of heat energy used. Okay, this is nice and easy. This is just putting numbers into an equation. So heat energy, okay, we need to calculate, equals 210, we've been given that number, times 34.8, honestly it's as easy as this, okay, 7308. And they've given us energy units. We've not been told what unit, but they've just said energy units. That's fine. Okay, next one. Okay, propanol. Propanol and butanol are both members of the same homologous series. Homologous series as ethanol. Don't worry if you can't say that too. You never have to say it, just read it. Okay, propanol and butanol can be burned in the apparatus shown in figure 3. So they can also burn a spirit burner. They're also alcohols. Okay, not the sort of type we drink, the ones that you burn, okay, and fuel. They'll be actually very, very poisonous. Okay, give 3 reasons why ethanol, propanol, and butanol are members of the same homologous series. So it means what they all got in common with each other. Okay, so there's quite a lot of things that you could answer for this one. So why are they in the same So they actually all have the same functional group. That actually makes them an alcohol and gives them that O sound at the end. They all have the same functional group. That makes them what group they are. They have the same functional group. Functional means a bit that does something. Group. So it's OH. Okay, that group. Okay, they're the same general formula. This is probably the one that you remember the best. Same general formula. Okay. Formula is CnH2n plus 1 OH, because they're alcohols. So alkanes and alkenes got a slightly more simple one than that, but same general formula. And another one is that they react. So let's talk about their reactions. If you don't remember about their formula, you can actually talk about their reactions. Reacts in a similar way with oxygen. So it's kind of like they're in a group, isn't it? Their molecules, so they will be in a series instead. Okay, so they react in similar ways. Or trend in physical properties you could have had. That'll give you marks too. So if you can't remember about the formulae, always look at that functional group though. That's a big thing. If you've got the same, and their names are similar too, that gives you a clue. That O on the end, that means they're all alcohols. Okay, ethanol can oxidize when exposed to air to produce ethanoic acid and water. Propanol could also oxidize in a similar reaction. Let's give you a clue to that, didn't it? When it is exposed to air. Write the word equation for the reaction when propanol oxidizes when it is exposed to air. This is easy, isn't it? Because we know that they're part of the same series, so it's going to be a pattern. Okay. We've got ethanol reacts with oxygen, so does propanol. So propanol plus oxygen. And what we told ethanol reacts, so to be ethanoic acid and water. So we do ethanoic, we get propanoic acid. You don't have to know what that is, you just need to know the pattern, plus water. That'll give you 2 marks, okay? Because really you just got the answer. So I said propanoic instead of ethanoic. Okay? What is the formula of the functional group in carboxylic acids? I love saying that word. Carboxylic acids. Okay, so OH is alcohol. Let's make some notes while we're here to remind ourselves of revision. That's an alcohol. That is a methyl group. Okay, that's methyl group. CO2 is sort of a carbon oxygen group. You don't see that at GCSE. This one, OOH, is the carboxyl group. This is the one we see. There are other groups that exist out there, but we don't see them at GCSE until you get to A level, and you'll start seeing things like ketones and things. We don't see those. So that's carboxyl. That's the carboxylic acid, COOH. Okay. Let's have a look at the next question. Figure 4 shows information about ceramic, like a plate. Okay, ceramic, and a metal. Can be used for other things, but it's probably plate is the most likely thing you would think of, or a vase or something. Flexibility, ceramic, low, yeah, they just shatter. Okay, think about a plate, you drop it on the floor. It doesn't bounce, it just kind of shatters, especially on tiles in the kitchen or something. Whereas metal wouldn't shatter like that. Hardness, medium, yeah, I suppose you can't really scratch it that easily. Metal, low, and on the metal, yeah. Reaction with water, yeah, no reaction, you can wash a plate. Metal, very slow reaction, because yeah, waters they do, don't they? They do react, even if they're not too reactive, they can react very slowly with water. Density, medium, metal, high. Yeah, they're not that, if they had a metal plate and it was solid, that would be quite heavy to pick up. The ceramic, rather than the metal, is more suitable material for wash basins. Yeah, like sinks, that means, because often they are ceramic, aren't they? Okay, give a reason for this using a property for figure 4. So you need to do 1. So wash basins applying water. So ceramic, okay, has no reaction with water. You do sometimes get metal sinks, but not usually in the bathroom where they use a lot. And even then, if you have a metal sink, it does react with water very, very slowly over time, and they get kind of a little bit sort of tarnished, don't they, over time? If you get a metal sink, if you've got one in your house, okay. But a ceramic sink doesn't tarnish like that; it doesn't react. So I'm going to stop video there, and I'm going to go and continue in part 3. So thank you for listening. I'll see you in part 3.